So welcome back to the second part of the 19th lecture. We have now seen in detail the spatial lag model, including its interpretations and impact on inference, right? So we are now going to move to this next popular form of a spatial regression model called as the spatial error model, or even called as the spatial autoregressive error model. Autoregressive error model. Those of you who are used to time series notation will be able to connect with it. So, in short, it is called as the SAR model. Okay. So, I'm going to start with motivation. I'm going to motivate this model before I get into the technical details of it. So, first, that this model, the SAR model, represents a situation where spatial dependence in the error term arises due to omitted random factors. Right? So there are some random factors that explain why, and we omit them, and they are now a part of the error term. Right? That's why this type of a phenomenon or this term is also defined as or termed as or defined as a nuisance. It's a nuisance spatial dependence term. Okay, and then it is employed in situations. It is employed in situations that are characterized. This is an important point. Characterized by a mismatch in spatial process with the spatial scale of observation. So if you are studying a process, a population process or a natural process which has very high resolution, which is very high resolution in nature, but the data that you have are aggregated in nature, right? Then such situations will be characterized by nuisance spatial random error, because there's no way for me to account for spatial process at the resolution that it actually occurs, right? I have data for something at district level, at state level, but the actual process, for example, crime. Now, the spatial resolution of how crime is observed might be much, much more finer in terms of the data are actually recorded than the data that are in public domain, right? In that situation, such a mismatch can never be accounted in a model. So it is going to enter into the error term as a random, disturbance, a nuisance term, right? And you can imagine, such a this type of a categorization is quite general. I mean, this is something that we encounter a lot of the time, and that is why spatial error model happens to be a very popular form of model, right? Right. So I'll give you an example. As an example, we can think about combining high resolution, let's say land use data, something that we have seen, that is, let's say, the Bhuvan data, right? And let's say we are combining that as a function of something like farmer education or farmer education disparity in terms of gender ratio. Things like, the dropout rates for boys and girls, the education levels, the skill development levels, and so on and so forth, the training that, let's say, women farmers have versus men farmers. So in households that have women heads versus, men as heads, or male members of a family as the head of the farmers, then you may have these systematic differences, and you might want to account for them in terms of how land use decisions are taken. But such variables are usually only available at district level, or at taluk level, at block level, at state level. Whereas land use, let's say with Bhuvan, is available at a very high resolution. So on the left hand side, I have a variable which is of the resolution of 50 meter by 50 meter, right? And on the right hand side, I have a variable which is at the district level. So there are many, many, many pixels of land use that are contained within one district. And this mismatch is going to cause, a random nuisance in my model, and hence, will make this spatial error model really useful. Okay. Finally, I want to just say that a spatial error process impacts the efficiency of estimates. Okay, right. So earlier we saw that, a spatial lag, version of it actually led to bias in the estimates. Here, I will not have the bias, and we've seen the reasons earlier why there is no bias with the spatial dependence in the error term. We saw that with much more, restricted form, right? Now we have a much more general form with the spatial lag notation, or the notion of spatial lags, right? Okay. So having understood this, let's move on to the mathematical treatment of a spatial error model. So the SAR model can be then written as the following. So we have a y equals x beta plus u, something that we are very used to. Now here we have variance of u given x is not equal to a situation which we are very fond of, where the off diagonal elements are 0, diagonal elements are exactly the same across all ui's. Right here, I'm not going to have that situation. Rather, what I'm going to have is that covariance of ui and uj will not be equal to 0 for some I not equal to j. I wrote this even when we had, earlier when we had just introduced the SAR model. Okay. Now, notation wise, we can write, note the variance of u given x. Again, u is a n by 1 term, so the variance by itself is going to be n by n. That's why I have I is n by n. Sigma squared is just a scalar, so it's just 1 by 1. I'm just checking, y is n by 1, x is n by k, beta is k by 1, so I have n by 1, and u is n by 1. So all consistent. Now this variance of u given x can be written as expectation u transpose given x. Okay. How is that possible? Well, u is n by 1, u transpose is going to be 1 by n. So overall, I have a n by n, which is the same as the matrix on the left hand side. What is being used in this definition is the definition of the variance. So variance of u given x, by definition, it's a little aside I'm doing for you, just in case people not have seen this stuff before. Variance of u given x is going to be expectation u prime given x minus expectation of u given x, the whole square dot product. Okay. Now this term is equal to 0 by assumption 2 of my regression model. Okay. So you can go back and revise the regression model where we did. So that's why I can write variance of u given x as just expectation u prime given x. Okay. And similarly, I can write the covariance as expectation ui times uj given x. It's not comma, expectation times ui uj is not equal to 0 for some I not equal to j. Well, it could also be all, okay? I mean, it could also be non-zero for all I not equal to j, but at least some, for some I, some of the off diagonal elements are non-zero. So what this situation, this second condition basically implies is that the off diagonal elements of the variance covariance matrix are non-zero. Okay, so we are, basically we are working with a non-spherical, variance covariance structure. Right, and I'm just using these terms because earlier when I had introduced the regression, we have done a review of it. Well, I've discussed all of these. What are non-spherical errors? What do we do when we have non-spherical errors? What's the impact? How do we reconcile these situations? You have to go back and revisit these things, again and again. So in terms of specification, I'm just going to say model specification. What we are saying is that we have y equals x beta plus u, where such that u is equal to lambda wu plus e, where this e is distributed normal with zero mean and a homoscedastic variance covariance structure. So this E is what we are used to when there is no spatial dependence in errors. And the spatial error dependence in errors is explained through the weights matrix, right? So now, this WU is nothing but the lag in U, because W is by itself a n by n, U is n by 1, that's why this UL is also n by 1. So it's a lag, just like we defined spatial lag for the outcome variable WY. Now we are working with this WU, right? So this is the spatial lag of the error term in parent regression. Why do I say parent? Why do I use this term parent regression? Well, I have two, you can think of two regression models. One is on the outcome variable Y, and the second one is on the error term, right? So U is the error in the first equation. In the second equation, U itself is dependent on its lag, and what remains is now a random term E, which is the homoscedastic error term, right? So E, this implies that E is homoscedastic. U is heteroscedastic, right? I mean, this implies U is heteroscedastic. So this is, all about model specification. So let's rewrite this thing and move forward with our analysis. So, we have y equals x beta plus u such that u is equal to lambda wu plus e, where e is normal, multivariate normal, zero mean, sigma squared in. Very quickly, my dimensions are n by 1, y is n by 1, x is n by k, beta is k by 1, so I have n by 1, good, and n by 1. U is n by 1, w is n by n, u is n by 1, so I have n by 1. Lambda is a scalar, right, so it's a 1 by 1. E is a n by 1, so E is n by 1, so its mean term, that is the distribution mean, population mean, is n by 1, and the variance covariance obviously will be a n by n, right. So, everything falls in line so far as I understand it. Okay. Now, we can rewrite the error structure. We can rewrite the error structure as under. So, I can say u minus lambda wu equals E, which implies I have u times, I n minus lambda times u equals E, right. Or like I did earlier, I could pre-multiply this by I n minus lambda w inverse, and I will be able to rewrite u. Okay. So, now my variance covariance matrix, now our let's see, the variance covariance matrix of u can be written as, okay. So, I am going to now say expectation x. So, I am putting the conditional as a subscript just to have a concise notation. U prime is equal to expectation of u is I n minus lambda w inverse u times I n minus lambda w inverse u, the whole thing transpose. Okay, I did a mistake here, right. I guess you will be able to recognize the mistake. Well, it should not be u, it should be E, because I am just writing the form of u, right. So, I have I n minus lambda w inversed E and then multiplied by I n inversed E transposed. Okay. So, I am going to rewrite this thing again now. So, I have this thing is equal, I am going to take the transpose of the second term. Okay. So, this is my, so I am going to just do that. So, I have equal to expectation I n minus lambda w, this will be written as is E. Now, this transpose will become E transpose I n minus lambda w inversed transposed. Okay. All right. So, I have done nothing, I have simply done this. Now, expectation, remember, is conditional on x. Now, this expectation operator is a linear operator, so it will start to enter the matrix form inside. I, lambda and w all are independent of x. So, the expectation operator can start to go right in, they are degenerate terms, right. So, I have this is equal to x I n minus lambda w inverse expectation E transpose times I n minus lambda w inverse transpose, right. Now, this expectation E transpose, well, first of all, this step is because expectation is a linear operator, okay, and expectation E prime is nothing but sigma squared I n, right. This is the variance covariance structure of the error term, right. So, I can now move forward and say this is equal to I n minus lambda w inverse sigma squared I n minus lambda w inverse the transpose, which can be written as sigma squared is a constant, it will come out. And what I am looking at now is sigma squared times I n minus lambda w inverse and I n minus lambda w inverse the whole thing transpose. So, let us work with its dimensions. I n is a n by n, w is a n by n, lambda is just a scalar. So, I am working with a n by n, The inverse of n by n is n by n. The transpose of a n by n is again a n by n. So overall, it is as if I have sigma squared omega as the variance covariance structure of the error term u. And this omega by itself is a n by n matrix, right? So this entity I minus lambda w inverse times its own transpose is what is characterizing the off-diagonal elements and spatial dependence through off-diagonal elements using the weights matrix. Okay, so I'm going to write it down in a concise manner that this term here, this characterizes spatial dependence through W and lambda. Lambda is to be estimated, but this is the term from where this idea of a spatial lag or notion of spatial lag is leading to a spatial dependent structure in the error variance covariance matrix. And the basic idea is that because I don't have sigma squared in and I have sigma squared omega, I can say that is errors are heteroscedastic. Right? This is something I'm very used to by now. I'm very used to in terms of characterizing spatial error processes. Okay, so I have a model. Which is y equals x beta plus u, such that u is equal to lambda wu, which is the ul term plus e, and e is a homoscedastic error with expectation 0. Okay, so this structure here implied that the variance of conditional variance of u, which is also expectation of u prime, can be written as sigma squared omega with non-zero off-diagonal elements, and these off-diagonal elements which are non-zero are characterizing spatial dependence through this interesting term I minus lambda w, which is directly sourced from the model. Okay, I hope this is crystal clear for all of you. Okay, all right. So with that, I'm going to move to the next step, which is obvious next step by now. It says it's the estimation. I want to now estimate the spatial autoregressive model or the spatial error model. Okay, so my next agenda is to estimate the spatial error model. So obviously, from what I've learned till now, you know what I'm going to do? I'm going to apply the FGLS strategy. And if you followed through the notes till now, FGLS strategy usually works in steps. So we are going to have steps here. I'm going to pronounce this step slowly. Step 1. What is step 1? Well, luckily, very good for us, because of the weights matrix characterization, we exactly know the variance covariance structure, right? So we are going to write that down. So we say we know the variance covariance matrix. Covariance matrix for the error term. All right, so what is the variance covariance matrix? It's variance of u given x is equal to sigma squared omega. We have seen the exact form of omega. We've written it down previously. This thing can be written is then can also be notated, something that we have used earlier, as a matrix sigma, right? We know that I'm going to rewrite omega okay. Now, sigma inverse, if I were to write sigma inverse, that will be equal to sigma squared inverse omega inverse, and that you can write as I minus lambda w transpose, because when we take an inverse, we flip the transpose. So you have In minus lambda w transpose times In minus lambda w, and a sigma squared is sitting right in front. Step 2, we are going to find a matrix T such that T times T prime times T is exactly equal to omega inverse, and T is a square, that is a n by n matrix. It is an arbitrary n by n matrix with this property that T prime T is going to be omega. Now, it is not so hard to see that T is simply equal to I n minus lambda w. Perfect. So, because I have this ready-made solution, in my step 3, I am going to define transformed dependent and independent variables. Okay, these are very logical steps in FGLS now. By now, we have looked at FGLS in multiple settings, and I believe that you will have a grip on why these steps are following the path that they are. If you don't, then you have to go back to previous lectures and revise FGLS. Okay, so I'm going to define Ym, which is my nu. So I can also, instead of calling it m, I'm just going to call it y nu as Ty, and x nu as Tx. Okay. Now, of course, by definition, T is 1 minus lambda w, y, and 1 minus lambda w, not 1, sorry, I times minus lambda w times x. I have to always check dimensions, so I'm going to do that. Y is n by 1, T is n by n, so y is n by 1, perfect. X is n by k, T is n by n, so x nu is n by k, perfect, right? And I just have to keep a note that this lambda, we need to estimate this term. Okay, so straightforward first 3 steps of the FGLS strategy. Okay, so let's go and write down step 4. Step 4. Well, step 4, we regress y nu on x nu using the maximum likelihood estimation strategy. This is something that we have seen as well in maximum likelihood. We declared the assumption. What the assumption was declared in terms of distribution? Sorry, we declared the distribution of the error of the random structure. What assumption did we start with? Well, we declared that E had a normal distribution. So we will start in my maximum likelihood estimation. We begin from there, right? So we know what? We know that E is multivariate normal, 0 mean, sigma squared, In variance covariance, right? Then the log likelihood function for estimation is written as ln L beta lambda sigma squared Yx. So I have my parameters of interest. These are all my model parameters of interest. I want to estimate betas, lambda and sigma squared. Of course, lambda is my important parameter of focus here, right? But for maximum likelihood estimation, I'll be estimating all these parameters, and at my disposal what I have is the data. I have some data and I have an understanding of the population distribution. I'm trying to fit the data using these flexible parameters so that the model fits the data in the best possible manner. Okay, so through this my algorithm says you have to maximize the likelihood of observing the sample given the population process, and in the process you will estimate beta, lambda and sigma squared. Remember, beta is a k by 1, so I have k different parameters. So overall, this means I have k plus 2 parameters to estimate. So at least that is the size of data strength that I need. So, if I have more parameters to estimate, more is the data, that I need to do that. And, you can go back and look at, any typical standard normal distribution based maximum likelihood estimation process for a regression. It is a standard, it has a standard analytical form, which is the following: y nu minus x nu beta times transpose y nu minus x nu beta. Okay. Now, interestingly, we have to always check dimensions. We have the first term is n minus 2. This is a scalar. N minus 2 log of sigma square, scalar, right? So, scalar 1 by 1, scalar. Here I see something in matrix form. So, y I know is n by 1, x is n by k, beta is k by 1. So, I have an entity which is n by 1. The transpose of this entity is 1 by 1, 1 by n, right? It is multiplied to then entity which is, we have seen, n by 1. So, overall, I actually have a scalar. So, it works out really well for me. So, all I am doing is I actually have a scalar representation on the right hand side. I have some unknowns that are betas, lambda and sigma squared, and I will simply write the first order condition and just go through with this maximum likelihood estimation process. In return, as a solution to the above, I will have beta hat FGLS, lambda hat FGLS, and sigma squared hat FGLS. This is the solution. These are going to be efficient estimators, right? We have seen this earlier. You can go back to the theory and learn from there. But these are all efficient estimators. So, lambda hat FGLS is our parameter of focus. It tells us the extent and the form of, the variance covariance structure of spatial dependence representation in the error term of a spatial, error model. Okay. So, having understood the spatial error model, its form, the motivation, why do we even study it? And we've seen that why it should be a popular, model form, right? And finally, coming to a point where we are able to figure out how to estimate this model, although of course it's a highly computational exercise. You will see in upcoming very soon we'll be starting hands-on tutorials, and you will see that the software, these softwares have a statistical software. You will see that estimation of a spatial error model is scanned, and so is the estimation of a spatial lag model. But it is good to know what's happening behind the scenes. So the theory that we see here is going behind estimation of the SAR model, right? How does the weights matrix enter? How does the the spatial dependence parameter lambda enter the entire story, right? So these are very important steps in terms of understanding the results that you will see from your our tutorial exercise. What I want to discuss for a little bit now is what is the impact of ignoring spatial dependence in model error. If I ignore spatial dependence, what I am saying is I am assume lambda equals 0 in previous discussions, right? So I am saying as if my error term has a variance covariance structure which is represented by an identity matrix. That is, off diagonal elements are 0, errors are spherical, the diagonal elements are exactly the same. If I assume that, and now my lambda is non-zero, which is what Anselin is showing us through this simulation. So now I'm looking at lambda as my parameter of interest, and as lambda increases, what happens to my beta hat? You see that when lambda equals 0, my expectation of beta hat is somewhere around here, and it remains there for all the cases of lambda. What is happening, however, is that for lambda equals 0.9, there is a very large error around the expectation of beta hat. And this error has gone up from considerably from the case where lambda was equal to 0, right? So what's happening is that so lambda equals non-zero, a spatial dependence in error term, is bringing in inefficiency into the model estimators, that is the beta hats, right? It's bringing the idea that the standard error of this beta hat will now become large, and it's going to become an imprecise and inefficient estimator, right? How do you go about reconciling it? The FGLS strategy that we have just seen before we saw this picture, right? Okay, so that's almost about, almost all about the spatial error model. I just want to talk about the variant, a variant of the spatial error model, which is called as the spatial moving average model. So this is called as also the SMA error model, right? So I'm going to briefly discuss it. The specification of this model is as follows. The specification is, okay, y equals x beta plus u, something I'm very used to, such that now u is equal to lambda w e plus e, where e is multivariate normal 0 comma sigma squared in. Instead of u being spatially dependent on itself in the neighborhood, now it is dependent on the lags of a standard normal process. Okay, so it's a variant of how in the random structure these off-diagonal elements are correlated with each other. As far as interpretation is concerned, why is it different? Why is it different, right? A question comes to us, why is it different from what we were doing earlier? Well, this setting, this particular model represents a very specific case when E represents innovation. And then WE is somehow the propagation of or diffusion of innovation, right? So diffusion of innovation, right? In social sciences or in technology, people are very interested in why are technologies adopted the way they are? Can we understand them formally? Can we measure the diffusion of why people buy certain types of apps from the internet, on the internet, or why do they buy certain models of phones, of computing devices, and so on and so forth? Such a model is able to explain such things. So this diffusion of innovation can also be termed as the smoothening effect of innovation on spatial neighbors. So it's a diffusion, right? So we are looking at how the neighbors are going to, get this effect, or how is it going to spill over to the neighbors. Okay, here, in order to understand how do we estimate these things, the critical entity was this variance covariance matrix sigma. Once you know the sigma, you also know other things, right? So sigma, which is nothing but variance of u given x, in this case is sigma squared I plus lambda w instead of I minus lambda w for SAR. For SMA, it's I plus lambda w times I plus lambda w transpose. Okay, so I would just mark out, notice this plus sign as how things are different. From here on, everything will follow through exactly as same as the spatial error model that we have just discussed in detail. Okay, so that's all about specifying spatial dependence through the error model of a spatial regression framework. Okay, so we will now sort of, by now you have developed a good understanding, a good hold of how these spatial processes are specified formally. How do we measure these effects? How do we estimate these from the data, right? So going forward, we are coming very close to the end of this lecture series. But and moving on to the hands-on exercises. But by now, we have formally used this device called the weights matrix in order to specify spatial dependence in either the mean outcome or the error structure, something that we started this module with, right? As a next step, we will look at some global measures of spatial autocorrelation using the weights matrix based notion of spatial lags. All right, and then we'll look at a couple of hypothesis tests, which will be strictly time permitting. But I will end this lecture here. Thank you very much for your attention.